Does a scalar have a direction property? We're normally told that scalars don't have a direction property and that vectors do have a direction property. And yet we have found that in a recent video that we were able to normalize a rotor, which consists of a scalar and a bivector part, by taking its magnitude and then by dividing by that magnitude to give its direction, which of course had a magnitude of 1, and that was the whole point. We didn't want something that would scale things as it rotated them. So it seems that we were kind of like well along the way to defining a direction for our geometric number. So what do you think? Welcome to the STEMCstudio channel and to another video in the Geometric Algebra First course. Of course, the purpose of this video is not to debate whether scalars have a direction property or not, although we will show that actually conclusively they do have a direction property. But the point is really that we are going to implement a magnitude and a direction method, both of them, on our geometric number because they are such useful concepts, and it'd be nice to have those convenience methods. And we'll also see that we can optimize those methods so that they will execute very efficiently. Okay, let's get to the theory. So here I've written down what the magnitude and the direction of a multivector are, and the magnitude of a multivector is the square root of this quantity in here, which I like to call the quantitude. It's the square of the magnitude, although the formal term in mathematics is the squared norm. The norm being the magnitude, so the squared norm is the square of the magnitude. In any case, you take the square root of this thing in order to get back to the magnitude. So the quantitude is equal to the multivector scalar product with the reverse of the multivector. And we've already implemented this scalar product. It's the SCP function, or we've operator overloaded it to have this vertical bar in it. It already works, and it works for scalars quite happily. So check mark against this, there's no problem defining the magnitude of a scalar. And that's no surprise because people always talk about, well, the magnitude of a scalar is just the absolute value of that scalar. What about the direction? The direction for our multivector we've defined to be take that multivector, divide it by its magnitude, which we can always do, and that will work providing the magnitude is not actually 0, because if we're dividing by 0, that wouldn't be defined. But if, on the other hand, it's non-zero, the magnitude, then we'll get a value for the direction. Come what may, it doesn't matter whether it's a scalar, a vector, or a bivector. And in fact, you can see that the direction of a scalar is actually just going to be either +1 or -1. Because if you take any number, say -10, and then you divide it by its magnitude, which is 10, you'll get -1. If you take +10, you'll get +1. Okay, so it's a perfectly well-defined quantity, and therefore we can implement these on our geometric number without any worries that, they're not well-defined for certain grades and that kind of thing. So let's go ahead and do that. Now recall that we actually implemented the magnitude function in the previous video, and so we're going to borrow this implementation, and then we're going to take it over to our geometric number so you can find yours. And we're going to implement this as a method. So in keeping with what I've got before, I'm going to put it in alphabetical order. I'm going to remove the function keyword there. So this is now a method. I'll just format it. And of course, we no longer take an argument. So I'm going to remove the argument. And now the thing that we're acting on is this. So I just need to make those replacements. And we are good. We've got our magnitude function. Okay, let me format that. Now, testing, I have implemented a magnitude test. So you can do this yourself as an exercise. I'm not going to walk all the way through this. You've seen testing before. So let's run this, and I'll hide the docs. You'll see the magnitude, it should compute that, and all of our tests pass. So we have the magnitude function implemented. Let's go ahead and do the direction function. So we'll put the direction in here, and that's going to return a geometric. And what is this? So it's going to be this dot divided by this dot magnitude. Okay, there we go. So if I could spell correctly, or I could return. Okay, that's the problem. There we go. Okay, and I also have some tests for this, so you can implement your own tests also as an exercise. So we enable those, and the direction, it should compute m divided by the magnitude of m. So far so good. Okay, so let's just do a quick code review of what we've just implemented. We can see that we're implementing the magnitude function by computing the scalar product, and then what we do is compute the reverse, or rather we compute the reverse and then we combine with the scalar product. And then we just take the scalar part of this quantitude and we take the square root and off we go. Now, looking at this, you should realize that a couple of things here. One is we are using operator overloading, and two, we're actually creating two temporary geometric objects that we just discard. I mean, the reverse is creating a geometric, right? If we click on that, we get that. And this is creating a geometric because we're basically creating a scalar product. So we don't want to do that. We don't want to create a lot of temporary objects because that could have an impact on performance in simulations. If you're calling magnitude many times, then you're creating a lot of temporary objects, and what's going to happen is the garbage collector, as it's called, in the browser is going to have to play catch up. In playing catch up, what it's going to do is it's not going to give you all of the frames for your animation. It's going to steal some frames from you, and so it can do the cleanup. So we want to be as efficient as possible. I think the second thing, and this is me speaking personally, but I want this geometric number to work whether the person who's consuming it is using operator overloading or not. Okay, because you may choose not to use operator overloading for different reasons. It is slightly more efficient to not use it, but there may be some other reasons. So, for example, you may be working in an environment where you can't have operator overloading. So let's make sure that we don't require operator overloading. So what I'm going to do is I'm going to turn off operator overloading now in this project. And of course the tests break because we're using it here, but we can also kind of like get them working again by just replacing that scalar product operator with a method call, and we're good to go again. So we've solved the operator overloading problem, but what we need to do now is we need to solve the efficiency problem of creating too many objects. So let's start with the magnitude method. The scalar product is the backbone, if you like, of this method. It's really, I mean, that's what's mostly what's happening here. Yeah, we call reverse, but the scalar product is probably the most complex part. And as you can see, this is what it does. It really just takes the left-hand side and the right hand, and it computes like grade products with a minus sign in here for the bivector part. Okay, so this all follows from the definition of what's the scalar product of a geometric number with another geometric number, and you end up with this. So we want essentially this, but we want to have a variant of it where the second argument is reversed. Well, reversion is only going to change the sign of this quantity here, and so that's going to make this minus into a plus. And so essentially, to get our full scalar product with a reversion on one side in, we really need just this computation here. So I'm going to steal that, and I'm going to bring it in here, and I'm going to replace the calculation that we have on this line with a new calculation that I hope will actually be more efficient. So I've got to be careful here. My right-hand sides now are this again. I don't want the minus sign in here because of the reversion. And then I want this again. Okay, so with that, I've computed a quantitude, which is now a number. And so I can replace this, which used to be a geometric, with just a quantitude. So great, we're successful. We're passing the tests again. Made a fairly substantial change there. And everything looks good. Now, I would say here that, this is a little bit difficult to read, number one. Number two, we're making property accesses here, which are just identical. This.a, this.a, this.a. So it would sort of make sense, I think, to try to replace these property accesses by something that would store them temporarily in a variable. So what we can do is make it a little bit more efficient by doing this. And a little bit more readable too, I think. And it's possible, of course, that a compiler might actually figure this out and it might actually make this optimization for us, but you shouldn't really assume that the compiler is going to figure everything out. All right, so there we go. We have now an efficient magnitude method. Let's go and check out our direction method and see if we can make this more efficient. Well, let's see. We've got division going on here, and this is division. And what we're really looking for, we know the magnitude is going to be a scalar, so it's actually just going to call this part. It's not going to use the rest, which we know that's used for like computing a ratio. So here what I'm going to do is I'm going to compute the magnitude still as this dot magnitude. And that's returning a geometric. So if I go and put an A there, then M is now a number. And now what I should be able to do is I should be able to take this calculation and use that. Of course, we don't need to initialize the first time because there's only one calculation that we're performing here. And so you can see that what we're doing is we're sort of unrolling or unwrapping the other implementations and picking out, just cherry picking exactly the part that we need to get the job done for us, okay? So now I've got my components, and all I need to do now is construct my geometric number. So I'll do that right here. And with any luck, we are still working. I'll just format the document. So this is better. It's better, but not quite there. We're still creating a geometric number because we're computing this magnitude geometric, and then we're just taking the scale apart. And if you look at the magnitude, well, there's a function in here which we would like to have access to, or it's this expression rather. We'd like to have access to this expression, but we don't. So what I'm going to do is I'm going to pull this expression out into its own function. So let's put it down here, function, and to be kind of explicit, I'm going to name it to tell you exactly what the return type is. And what I want to do now is I want to go back to my magnitude. Yeah, I want to grab this and steal that as the implementation. So we'll drop that in here. And we're going to return this here, and this needs to be replaced by MV. Okay, the argument, the multivector argument. Okay, so have we got it? Let's just set that out. Oh, don't need an equals in there. Thank you very much. And this, of course, is just saying we've declared it, but we're not using it yet. So let's go use it. So we come back to our magnitude, and we want to have quantitude as number, and we want to put in this. Okay. So we've kind of now got a reusable function that we can use in the direction. But we also need the magnitude, so we're going to need to do math.square root, and then it's going to be quantitude as number, this, and that should work. Okay, so we're almost there. Now there's still some common code here. We're doing this square root of a quantitude as number, and we're doing a square root of quantitude as number. So it also makes sense that perhaps we have another function down here, function magnitude as number, and that's going to take our multivector like that. And what this will do is we're going to return the square root of the quantitude as number of the multivector. Okay, so again, this function is not used. We come back in here and we go to our magnitude, and now we don't need this math square root. We just need to call magnitude as number, get rid of the parentheses, and we're good there. And for direction, we want to do the same thing. Magnitude as number, and we're good there. Okay. Now, let's see, for the direction, there is going to be a case where m could be 0. What exactly we should do there, I'm not going to cover that just yet, I think. But what's going to happen if this does turn out to be 0, then we're going to get not a number for the various components. But we'll live with that. Okay, so tests are passing. We've got the direction, we've got the magnitude. So let's now sign in so that we can upload this. So we're going to upload it to GitHub. Okay, and now that we've uploaded it, we will be able to pull it in inside our other project. So we go back to Flatland, and we've got E2GA as a reference. So now what we can do is we can pull references, and let's go back to our main line here. Actually, let's just check our E2GA. And if you look, yep, there's direction, magnitude is number, very nice. Got the functions, the extra functions in there. So we should be able to use this. So let's come in here. We've got body.r is body.r direction. And that's because I've actually tested this already. That's exactly what I want. All right, so we run it, and we don't want the printouts. And we'll get rid of the documentation. And we don't need the magnitude method anymore. And finally, what we want to do in here is we need to get some rotation going. So we need to give it some torque. So let's put in, say, 10 units. And we'll let this thing get some speed. And what should happen, of course, is that the magnitude of the rotor doesn't change. And we're all good. So that's it. So in this video, the amusing part is we have seen that you actually can define a direction for a scalar, and it just turns out to be plus or minus 1 according to whether the scalar is positive or negative. And it can be undefined if the magnitude of the scalar is 0. But there's nothing special about that. If the magnitude of a vector was 0, then its direction would also be undefined. So we've got a slightly improved geometric number with some nice convenience methods. That'll be useful to you, I think, going forward. Say, for example, if you're calculating rotors, it would be very easy to just define two arbitrary vectors. You don't care whether those vectors are unit vectors or not. You take the direction, you'll end up with unit vectors, and then you can get the rotor, which will rotate from, well, it'll rotate actually by twice the angle between the vectors. But the idea is you can create unit vectors, and you can also calculate the magnitude. I hope you enjoyed that. I will see you soon in the next video. Take care. Goodbye. Happy coding.